Here's a problem involving displacement. A bird flies 5 meters south, then it flies 3 meters west. First, we draw the resultant, or total, displacement. Well, you may be tempted to draw the southward displacement and then connect to it the westward displacement, but you'll notice I've made two mistakes here. First of all, when I drew my arrows, 3 is not longer than 5. This is the bigger value, so that arrow should be longer. The second issue is our convention is to draw the x-axis first and the y-axis second. So I technically can solve the problem this way, but being consistent requires that I do x first, y second. Okay, let's try again. Here's the westward displacement. That's a delta x. I know it's a delta because it's the change in x location. And then there's a y-axis displacement, delta y. Delta x is 3 meters. Delta y is 5 meters. The resultant displacement starts at the very beginning, it points to the very end, and here it is. I'll call that delta r, or you could call it delta r total, if you prefer. Now, you may be wondering, shouldn't we make this -3 and -5? Well, the answer is yes, we should, but because we have arrows showing the direction, those negatives really are already accounted for. Now, I drew the resultant displacement, but I'm missing something in my label. Displacement is a vector, dmv. Whoa. Every vector has direction and magnitude. So this stands for the magnitude. Where is my direction? To show the direction in my picture, I have to start at the x-axis and then draw an angle pointing at my vector. That'll be part of my answer. Okay, part B says, find or calculate the magnitude of delta r, the resultant displacement. So the magnitude is exactly that, delta r total. Notice part C says, find the direction of the resultant displacement. So C is asking for the angle theta. Where does this displacement vector point? For part A, we can use the Pythagorean theorem. We know that delta r total squared is equal to delta x total squared, or sorry, delta x squared plus delta y squared. This is a right triangle because x and y are perpendicular. So plug in the two sides, 3 and 5, and solve. Don't forget to square root both sides to get rid of this square here. And what do we get? We get 5.8 meters, right? Notice we round to 2 sig figs because that's how many sig figs the givens have. So I count 1, 2, and I round my value to the first decimal place, 5.8. To find theta, we will use inverse tan. Inverse tan always has opposite over adjacent. So if I look at my angle, I draw a line out from the angle, and that line will run into the opposite leg. So the opposite is 5, and the adjacent is 3. The hypotenuse is not a leg at all. That's the hypotenuse. So my angle calculation will be inverse tangent of 5, the opposite, over 3, the adjacent. When I calculate, I get 59 degrees, but I'm not done. I have to describe the rest of the direction. So what's my reference? Well, here's the beginning of my delta r vector. There's the tail. Okay, I visualize north, east, south, west. Which of those 4 things does this angle marking touch? The answer is west. So I'm 59 degrees of west, or from west. But which way of west have I gone to get down to delta r total? To get down to delta r, did we go north of west or south of west? The answer is south of west. Okay. Now this next problem, we're not going to solve it all out, but I do want to point out a harder type of problem that exists. We have a bird that flies 5 meters south. Okay, that's a delta y, because south is the y-axis. Then it flies 2 meters east. That's a delta x. Here's another delta y. We'll call that delta y2. And here's a second delta x. So the first thing is to draw the resultant displacement. The trick here is you have to find the total on the x-axis and the total on the y-axis before you get started. So just add up the x-axis displacements, add the displacements on the y, and what do we have? On the y-axis we have -5 because it's south. Then we have +11 because it's north. On the x-axis we have +2 because east, -6 because west. So this is -4 meters is the total x displacement. +6 is the total y displacement. Whoops. There we are. So now if I want to draw the total displacement, you know, this and this together, what do I do? Well, let me draw delta x total. It goes 4 meters to the left, or to the west, I should say. And then delta y, we do our x-axis first, our y-axis second. Delta y, whoa, hang on, delta y is positive, so my arrow should go up. So 4 meters over, 6 meters north. And then my total displacement is from the very beginning, tail to tail and tip to tip, from the very beginning, pointing to the very end. There's delta r total, but of course I have to mark theta as well, and I'm marking it from west. Part A of this question asks for the magnitude of the resultant displacement. Part A is asking for delta r total. And this is pretty straightforward. We use the right triangle, Pythagorean theorem. The only difference is now the x and y legs are the total values, right? Because there was more than one displacement on each axis. That's the only difference. And we work out the math. For theta, we use inverse tangent of opposite over adjacent, which comes to 6 over 4. And then whatever that angle value is, the rest of the direction would be to the north of west for this angle. So this is part B, the magnitude. C was the direction, which is this entire answer. It's the angle plus the north of west. The last thing I want to point out, if you know the time, 10 seconds, we can find the average x velocity by doing total x-axis displacement over time. We could find the total y-axis velocity by doing the total y displacement over time. And we could find the two-dimensional velocity by doing the 2D displacement over time. And so we would use the answers from above. We would use this as the x, this as the total y displacement, and whatever we got for delta r total, we would put that value here, and then the angle for this velocity would be the same as the angle for part C. Because if you walk at, I don't know, maybe it's 14, who knows? It won't be 14, but if I walk at 14 degrees north of west on average, my velocity is in the same direction. So this velocity vector has the same direction as this displacement.